Okay. Welcome everyone. Here we are already in May. I'm going to go through the initial introduction again, overview of the project and everything. And we'll quickly get to Stroud updates and then we'll go into John Jackson's presentation. So for any new folks, this meeting takes place every third Thursday of the month, 2:30 to 3:30 every time. This Zoom link is the same every time. If anyone is not on this distribution list, this email distribution list, please let me know and I'll put you on that. And as I mentioned in those emails, you can feel free to send those invitations on to others that might be interested. So attendees are generally in two groups here, those working directly in the Delaware River Watershed Initiative and those that are just working in the Delaware Basin but are not directly associated with DRWI. We are able to support groups that are not directly associated with DRWI but are just working in the Delaware Basin, so keep that in mind. We're also supporting the effort via DRWI and CSAW, the Consortium for Scientific Assistance to Watersheds. So here's the DRWI site, 4 states, 1 source. Feel free to check that out. CSAW address if you want to check that out. Goals for these meetings, simply time and space to check in, ask questions, report issues. I'm going to provide updates here. We also do a presentation every time. Today, as I mentioned, John Jackson is going to be talking. Main Stroud folks involved with these meetings, myself, Rachel Johnson, Krista Reeves, and Shannon Hicks, and then Master Watershed Stewards Carol Armstrong and George Seeds. The meeting is being recorded, so please just keep yourself muted unless you're trying to speak up. And these all are recorded, as I just mentioned, and they are posted at this address. There's a lot of other resources at this address. So today's agenda, I'm going to do updates first so we can get those out of the way so that we can just have discussion and questions after John's presentation. So just a little more overview. The primary goal from Stroud's perspective in doing these monthly meetings and supporting the users of these EnviroDIY stations across the basin is to support station owners in using the stations for their own local purposes. Secondarily, we are doing internal analyses of the data and trying to build out some watershed characterization templates that can easily summarize continuous data for groups to use in their local contexts. So moving to updates here, we have an EnviroDIY troubleshooting workshop scheduled for June 23rd, 1 to 4 p.m. So I would like to, I'm going to get out of this screen for a second and I'm going to paste this into the chat so that anyone who's interested can have access to that. My chat will come up. There it is. Okay. So feel free to copy that out and fill that out on your own time if you'd like to attend that workshop. Okay. Other update, there's a new quick guide at this resources site under the quick guides menu. You can see here, you can click onto it. It's a PDF and it simply lays out 4 different types of roles and responsibilities that we're sort of are recommending for managing these stations. And here it is. You won't go through the details here, but sort of some roles and responsibilities for a station manager or owner, basically overseeing these other 3 types of roles. Desktop monitoring of Monitor My Watershed, so keeping track of the station function via Monitor My Watershed, sensor cleaning and maintenance, and then quality control. So feel free to access that. Seems like it should be a nice little guide for folks in assigning responsibilities and roles and such. Okay, there's a new blog on EnviroDIY. It's a firsthand experience write-up by Cheryl Nolan. She's actually outside of the Delaware Basin, but it's a nice write-up about her personal experience in building one of these stations for the first time. The Broadhead Watershed Association is also going to be writing a blog of this nature up, so keep an eye out for that. And there's also some new posts on Manage My Watershed. There's a really nice interview by Carol Armstrong of Pete Goodman, who's a prominent member of the Valley Forge Trout Unlimited. And then there's an article here, two-part article here that I wrote for a fishing group a while back and that we posted here. And then some technical updates. The cell boards are, as a lot of folks know, they're fairly volatile. Some are frying pretty quickly. Shannon and Sarah are diligently working on a new board, and they should have some information on that very soon. Feel free to reach out if you have any questions, but hopefully in the near future, there will be a good replacement for those boards. And then just an update, as many folks probably saw, Monitor My Watershed was down for, I think it was almost 2 weeks, which was by far the longest it's been down as far as I remember. It is up and working again. Limnotech and Anthony Oftenkamp, they did a lot of troubleshooting and got it working again. You can check out the EnviroDIY forum, go to @Oftenkamp or this specific forum link, which I will again post into the chat here. It'll come up. Doesn't seem to want to come up for me. There it is. Okay. And I think that does it for me. Any questions at this point?
Oh, yes, I have the data upload. I tried a manual data upload, Dave, and still didn't work, even though everything else.
Okay,
so,
Jim.
Is something changed or what?
When did you try that, Jim?
Yesterday, I checked, everything seemed to, spark plots were working. Everything seemed to be up and running, but I tried to upload our file since my 2G has failed. So anyway, I was trying to upload the data. Right. And it didn't work. It just failed after sitting there for a while.
Okay. That's the first I've heard about that. Shannon, I don't know if you have any input on that, but I might just reply to that forum link that I just posted in there, Jim, and just mention that and see what they have to say about it.
I mean, there's a chat from Zach Malsberg about this, a script that Sarah shared.
Okay, well, I'll tune into that then and follow up on it.
Yeah, I would post to that forum, Jim, and see what input you get back, because this is the first I've heard that the upload is not functioning, although I'm not surprised. And Zach, if that did work for you, then send me and Sarah an email, and we should probably write that up as a blog so that the usage of that script that Sarah did can be accessible to others. So let me just share my screen once more and just note that we have John Jackson here. He's going to talk about water temperature. We're through with updates, so once John is finished, we should have plenty of time to discuss and ask questions and such. Okay, so John, if you want to share your screen and take it away. John, you are muted if you're talking.
My question is that full screen for you guys?
Yes, it is.
All right, good. So just so you know, those of you who've, first of all, welcome. Welcome to summer, it seems. Good day to talk about temperature. I've taken the presentation that I did several months ago and reworked it. This is only a portion of it. I thought I had done too much, too fast. This is really going to be an introduction to thermal characteristics of stream and or water. And then ecological implications I'll do at a different time. So one is how to talk about temperature. You've got thermometers out there. How do you look at it as how does it fit into the world that we live in? And then what does it mean in terms of changes in biota and things like that? I'll do a different time. So why is temperature important? I'm going to do this in 4 steps. One is about variability, temperature varying temporally and spatially, day and night, winter versus summer, mountain versus valley. Then I'm going to talk about how we've polluted the thermal regime. In other words, power plants and factories with point sources, could be big dams with a top release versus, which would be hot, versus a bottom release dam that would be cold. And then we have the multitude of habitat modifications, deforestation, small dams, urbanization with its hard surfaces, stormwater ponds, pipes, all changing the thermal regime. And then finally, climate change. And I do climate change last because all the other stuff I've just talked about is already happening, and it's happened in a big way. And climate change is going to come on top of that. And so that's just something to keep in mind. So the first thing that I've added here is a little discussion about a physical characteristic of water, its specific heat, its ability to absorb energy. So many of you might know what specific heat is, but I'm guessing a bunch of you don't. And basically, specific heat is the energy it takes to change temperature. And a common way of talking about it is in the calorie, where you take, if you apply 1 calorie of heat, you change 1 gram of water 1 degree Celsius. That's where calorie comes from. That's the 1 for specific heat. Different materials have different abilities to absorb energy or absorb heat without changing temperature. Water changes temperature very slowly. It takes a lot of energy to go up 1 degree. A metal, for example, takes very little energy to go up 1 degree. So here's another way of expressing it. And here's a chart where liquid water takes a ton of energy to change its temperature 1 degree versus dry air versus, I put in an arrow here, granite or concrete would be right in here around 0.88. Sand is down here about 0.3. So why is this important? This is why when you go to the beach and it's a bright sunny day and the ocean water is still cold, but the sand is too hot to walk on. It's because the sand absorbs that heat and changes temperature very quickly, whereas the water absorbs that heat and changes very little. And that's specific to hydrogen bonding in water, that H2O. Sun goes in, breaks some hydrogen bonds, they quickly reform, heat absorbed, no change in energy, no change in temperature. Your metals, your sand, your soil doesn't have that advantage. And therefore the energy of the heat of the sun ends up translating into energy or temperature changes in the substrate. When people go to space and they're looking for signs of life, they look for water. Water is essential for life, but it's also essential in that it provides a very stable thermal environment. In all likelihood, life didn't evolve on land, in part because of the temperature variations that can occur on land, and those interfere with a lot of your physiological processes. So if you've looked at your thermographs, if you've looked at your data, you realize temperature varies within a day, and it's different between days. So the red lines here are a small lake, and the blue line is a large lake. And this is just a comparison of different days. And the big lake changes temperature very little, less than 1 degree up or down, whereas the small lake is going up or down 4 degrees maximum. And here it is strung out over several days, and you can see the small lake going up and down and up and down, and the large lake not. And that's because, remember, maybe both of them are receiving the same amount of energy per square meter, but you're warming up a huge body of water in the large lake versus the small lake, and that therefore it cannot change temperature quick enough. The volume of water exceeds what the sun is applying. We also see that seasonal variation. These are some data from White Clay Creek here at Stroud, from different locations in the same watershed, all upstream of the Stroud Center. This is a calendar from January to December. The letter A, this straight line here, that's groundwater. That's what comes right out of the springs, or what we would find in the wells. And around here, it's averaging about 53, 54 degrees Fahrenheit, 11.3 degrees Celsius. These are expressed as degree days. And so you just take that temperature, 11 times 30 days, and you've got 330 degree days, 330, 360. It's just a way of counting accumulated heat. In the groundwater, it doesn't change. The ground, the plants, it protects it, it stays very stable. B is just the outflow of the groundwater, and B warms up a little bit, cools down a little bit over the year. By the time you get down to F, which is a third order downstream segment in say a meadow, you can see how much it warms and cools. So in January, it's quite cold, and in February and March and April, it slowly warms up until July and August. It's running quite warm, and then it cools down again. All the same stream, different locations. So it's location, 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 and that affects your ability to characterize. The one thing that is kind of interesting in terms of accumulated degree days, you notice the site, these different sites accumulate degree days the same, more or less, 4,200, 4,300. So all of this variation averages out. It gets warm, but it's also cold. That's how we maintain life histories throughout the watershed being synchronized. This degree days is a way of telling time. But the larger the stream, the more variable relative to the small stream, but that's only to a point. And that has to do with, again, the volume and stratification and things like that. I think I skipped a slide. We'll go back to lakes, and density of water has to do with temperature. And those of you who've ever swam in a lake that has stratified, the warmth of the sun warms the upper limnion. It's warmer and therefore lighter. The light water floats to the top, and it creates a boundary layer between the top and the bottom. So the top circulates and the bottom circulates, and the temperature change occurs in the metalimnion. And the amount of wind that blows, bigger the lake, the less likely it's going to turn over. It's just too much mass of water. You go to autumn, temperature of the air decreases, wind can turn over the lake. You go to the winter and you may get stratification, but it's due to cold, where the surface is actually colder than the bottom. Then in the spring, it turns over again. That's pretty common for lakes or even ponds. The only difference with ponds is the wind can turn it over. With that stratification, you get these massive temperature differences. So this is a warm lake and this is a cold lake. These are the months of the year, so January to December. The dotted line is air temperature. In the warm lake, you'll see the surface warms up just like air temperature, but the bottom of the lake, it stays very stable, very, very stable. And that's because the heat on the surface doesn't reach the bottom. It's caught up in the thermocline. The cold lake is very similar, warmer at the top, cooler at the bottom. Oh, so the 10, 20, 30, 40, those are depths. Those are meters of depth. So this is a pretty deep lake at 60 meters, 180 feet. Same thing going on here, but in the cold lake, this is air temperature. Notice how cold, say this is Minnesota, it gets very cold, not quite so warm, and then very cold again. But we see the same stratification, warm water at the surface, cold water at the bottom. The difference here is the surface actually gets colder. The sequence never really flips in the warm lake. In other words, the surface is always warmer than the bottom, whereas in the cold lake, you actually can be warmer at the surface than you are, or colder at the surface than you are at the bottom in the winter. That's the ice formation. This figure shows you the difference in ground temperature, groundwater temperature. I put them both in here so that you have Celsius as well as Fahrenheit. In case you're wondering, here's where we are in southeastern PA. Remember what I said? White Clay Creek is about 11.3. You notice the regionalization north to south. And then there's some elevational gradients that go along with it. These being mountains over here, changing the banding as opposed to out in the Great Plains where it's just a north to south pattern. So when you're going to talk about what's normal temperature or what's groundwater temperature, it depends on where you're at. And the truth is if we did a finer scale, there's quite a bit of variation, for example, in Pennsylvania between the mountains and down and the edge of the coastal plain or the edge of the Piedmont. We went through this one again. Where did I lose the graph? I'm going backwards. There we go. Stream order is the same as the size of the lake. So when it's a small stream, right out of the ground, it's groundwater. And the diel or diurnal change, in other words, coldest in the morning, warmest in midday, is nearly zero. And the reason why is because it's groundwater coming straight out of the water, out of the ground. It doesn't change. By the time you get to a third or fourth order stream is when you hit maximum daily or variation between morning and evening. You can hit 10 degrees, sometimes more depending on the day. These are averages. But then you start getting bigger and bigger. And you remember with the large lake, you start having too much volume. It's too hard to change, takes too much energy to change the temperature. So by the time you get to the main stem of the Delaware or the main stem of the Susquehanna, you're out here in 7th and 8th order, and you're only going to see quite often 2 degrees, plus or minus 1, plus or minus 2 degrees C in a day, warmest versus coldest. So your expectation for the diel change has to do with the size of the stream or the size of the pond or the combination. The second thing I wanted to talk to you about is the people changing those thermal regimes. People have changed it by thinning the forest, fragmenting the forest, or completely removing the forest. We've turned running water into standing water. In other words, instead of being a stream, it becomes a pond or a reservoir. We've urbanized areas that become heat sinks because remember that inorganic concrete and brick holds heat much better than a forest, than wood does. And finally, we started dumping effluents, industrial municipal effluents. They're discharged into the stream. They generally are warmer, either because they were inside, because they were used part of a process, or in some cases, they get dumped to ponds and then to the stream, and they heat up more during that pond phase. So let's look at deforestation. These are some data out of the Amazon. It's just an example. This is for a single day from 9 in the morning till 7 at night. The difference between having your thermometer in the open deforested reach versus down in the woods. The difference on average in a single day was 3.5 degrees C. Depends on the site, depends on the climate, depends on the days. It's hard to say, oh, you deforested, it's going to go up. Depends on a lot of different things. And you're going to hear that from me repeatedly. It depends. You have to know your system. Deforesting around the Susquehanna doesn't change the temperature much. Why? Because it's open anyway. It's a wide river. This was an experiment that was done in West Virginia where they took 6 different streams, 3 where they cut down half of the trees, and then another one where they cut down 90% of the trees. And this is distance from the downstream spot. So it's 100 meters or 150 meters open, then 100 meters closed, then another, or 250 open, 100 closed, 250 open. So your cold water comes down, it hits the open area. If the canopy is partially open, it warms up a little bit. If it's wide open, it opens up about 2 degrees. Cools down a little bit. In both cases, when it goes back into the woods, when it comes back out, it warms up again, especially where it's open. The difference here is either 2 degrees or 4 degrees. So cutting down the forest on these streams in a single day on average resulted in the summer over a 1 month period, I put in the details over here for you, added between 2 and 4 degrees C on average to the temperature. That's a climate change kind of change, 2 degrees, 4 degrees. We already did it just by cutting down the trees at this site. These are those same data, just plotted the frequency that you observed certain temperatures. So these are just proportions. And in other words, you saw the very few of really cold temperatures and very few of the really warm temperatures and a whole bunch in the middle. The difference between the reference, which is in the black, versus 90% tree removal, which is in the gray, you can see how everything warmed up. It shifted to the right. Versus the 50% tree removal, it shifted very little. What does that mean? Well, here's how it pops out at you. The black bars are sticking out up here, and the cooler temperatures, so the references were more frequently cool, whereas the treated or the deforested site was more clearly warmed. The other thing that you can see is notice all these very warm temperatures. In the 50% deforestation, you don't see those extremes. So not only are you warming it by deforesting, but it's a matter of how much and for what was your distance. If you deforested a longer distance, you got more heat added to the system. So you reached warmer temperatures. So that's a deforestation example. We mentioned this before about lakes varying with depth and the surface turning over. Well, when you take a lake, that's also true when the lake becomes a reservoir. And the key to the impact of a large reservoir has to do with the time of year and how the dam operates. So this is a dam, the McKenzie River. The light blue line is just the upstream of the dam. That's normal river temperature. The dark blue line is the temperature downstream of the dam. This is what it's releasing downstream. And in the middle of the summer, what they're releasing is much colder than normal. By late summer into the fall, the reservoir has finally warmed up and they're releasing water that's much warmer than normal. That's a typical dam effect. But the actual response you're going to see depends on the reservoir size and how it operates. But you could see this exact same pattern in the upper Delaware River, for example, based on how the Cannonsville is being operated. Embedded in that is, in many cases, dams, for example, are being used for hydroelectric. And in many cases, but less than it used to be, they operate by hydropeaking. They operate by on demand. It's less dramatic than it used to be because they've realized that this can have a very negative environmental impact, but quite often it had more to do with how they dried out the riverbed. And in many cases, because water was valuable, they turned off the spigots and the river would go dry. This one is obviously holding, this is an example from Austria. These are some data from the Shasta River in California, just to give you an idea of how the pulsing goes from warm, hydroelectric time, generate electricity, you get, or from cold to warm, then back down to cold. Same thing true. You get the same pattern if you're doing a power plant operation, if you're not using cooling towers, dumping hot water, then cold water, then hot water, then cold water. In this case, this example is operating at it's changing things about 9 degrees Fahrenheit on a daily basis, up and down 5 degrees Celsius. A lot of this has to do with where you're grabbing your water. So remember, a reservoir is just a lake with a dam, and it stratifies when things get hot. And you have your hot water at the top. The blue line here is the temperature. So it's warmer at the top, then it goes through the thermocline, and then it's cold at the bottom. This is oxygen, and oxygen is a problem in this case because the bottom of the lake ends up being anoxic. So if you want cold water, you're also going to be releasing water that's low in oxygen, but full of ammonia, hydrogen sulfate, heavy metals like iron could be dumping out. Modern dams have selective withdrawal points, and they do some mixing to try to reduce the thermal impacts, but also reduce the oxygen impacts. Before, it was all about recreating a cold water or the ease of keeping and maintaining your dam, and they did a bottom release, came out cold, but with no oxygen, and you ended up with fish kills as an example. Part of the effect of the dam, though, depends on where you're at. This is true for large dams like the Keswick River on the Sacramento. This is a thermograph from right below the dam versus about, say, 100 kilometers downstream versus over 200 kilometers downstream. It comes out generally, air temperature is here in orange, whereas the Keswick real data are right there in yellow and blue. Obviously, right out of the dam, it's running cold, much colder than normal. But as you go downstream, that river water picks up heat. And so by the time you're 200 kilometers downstream, you've picked up a lot of heat and you're starting to mirror air temperature, and you're probably much closer to what would be normal operation. We've been looking at a small stream right here near the lab by Longwood Gardens, Bennett's Run. We've been measuring temperature for a little while. It's a small stream that's complicated by a series of ponds that actually are in the headwaters, right up here above the first red dot here. This is an aerial photograph, shows you where our two sensors are running through the woods, and then two ponds, and there's actually a third pond right up here. So the main stem starts here, but it goes into this third pond. That's important because the stream coming in right here goes through this dam, all the actual water additions. Well, remember, warm water is lighter. So the cool stream water comes into this pond, sinks to the bottom, pushes out the hottest water in the pond, and that forms the stream water coming out of this series of 3 ponds. To interpret this, we've added some reference sites, and one I'm going to show you here is up from the Cheslin Preserve. It's not completely forested, but it's a wild trout stream, and you know it's probably only 15 kilometers from the Bennett's Run. Here are the 3 data streams. This is from 2018. The red line is upstream, right out of the dam. Blue line is down at the base of the woods. The green line is our reference, our Cheslin reference. This starts in May or June and goes all the way till almost the beginning of December. Obviously, the dam water is running quite warm. The woods are running cooler downstream, but not as cool as our trout stream reference site. So what we have, because we have the defining our starting point, the Cheslin Preserve, the pond effect is the difference between our upstream site and Cheslin. And on average, it's 7.5 degrees during this warm period. 7.5 degrees, almost 14 degrees Fahrenheit, warmer than it would be under natural conditions, say. However, we reduce that thermal impact by having almost a kilometer of forest. Out of that 7.5, we take out 4.9. So we cool it with shading almost 5 degrees. We take out almost 2/3 of the warming just by running it through the woods. So that shows you the positive impact of having that forest there at helping cool what's already a thermally polluted water source. This is a similar study a friend of mine did up in Massachusetts. She and her students had a bunch of sites throughout Massachusetts. They measured daily temperature every 15 minutes, 30 sites over 1 to 4 years. This is the annual calendar from January to December. These are small dams. 3 were beaver dams. The rest of them were man-made dams, but they're low head, 15 meter or less. So 15 or relatively small dams. On average, these guys warmed up the stream anywhere between 0.5 and 1.5 degrees. But note, this is the significance with the asterisks. That means upstream to downstream. All of these streams on average warmed up beginning in May and continuing to October. So that on average, the dams had a significant effect. The overall magnitude of the effect depended on the dam. So here they plotted just individual dams, where some dams had no measurable impact. One actually was cooler downstream than upstream. Others warmed up 4, 5, almost 6 degrees. Remember, we were warming up 7.5. It was the pond in Bennett's Run, and it may be because there's actually 3 ponds. It may be a number of things, but what they found is the magnitude of thermal change depended on the height of the dam, which ties to the impoundment volume, which also ties to how wide it is, the amount of widening, so how much solar radiation it's picking up. Also, it has to do with impoundment residence time, how long the water sits there, how many days does it take to replace the old water with new water, and watershed forest cover. And this last one is kind of interesting because we go to this slide. They plotted the sites here, but they plotted them based on starting temperature, upstream temperature versus, and then they plotted how much the temperature went up. If you started with warm water, the dam didn't have much of an effect. In other words, you were already warm, it didn't change much. The colder you were, though, the better chance you had of changing. So you went from cold water to cool water. Each of these, there's variation there, but the most important thing is all the sites that changed started out relatively cool, cooler than average. The last thing about this thermal impact, and this is very similar to Bennett's Run, they measured how far the heat signature was evident, the footprint. And that's basically how quickly can you dump this excess heat either into the air or into the ground. On average, it took them 1.3 kilometers to get rid of their excess heat. However, they did measure sites just like us. Now remember, we dumped 5 degrees in less than a kilometer. So we'd be right in this range here, the 4 degrees. And it took about a kilometer. So we're in this distance here at Bennett's Run. Our results fit in virtually the same as theirs. The key is water volume, velocity, and shading. You're going to get less cooling if you don't have the forest there because the sun's going to keep putting heat in. Last thing, urbanization. this one is probably least well known, and probably most complicated. But the bottom line is we do know urban areas tend to be warmer than non-urban areas. That's the heat island effect. Any of you who've ever visited a city in the summer that was very rural outside, you can feel it in Denver, you can feel it in Phoenix. It's cool out in the country, and as you hit this wall of heat, and that's just the heat that's held by the city being slowly released long after the sun has gone down. It's the middle of the night. You can still feel the heat being radiated out of the concrete and bricks and asphalt. As a result of that, urban streams tend to be warmer than normal also. Warmer than normal as in a forested area. Part of that has to do with what urbanization is. It's roads, it's pipes and ponds. So all of your hard surfaces, whether it's roofs or parking lots, anything that's been deforested in essence tends to be warmer. You also have all of your standing water that you create in the urban area, either for artistic purposes or as part of stormwater. They're behaving again like a dam and warming up the water. So both the hard surfaces and standing water warm the stream. You can also cool and make the stream behave more like groundwater, and that's by putting it in pipes. When you put it into pipes, sun doesn't get to it, and you can have miles of stream that's basically operating like groundwater. I threw this in because it's local. This is the historic map of streams of Philadelphia. This is what it looks like now. These are where the streams are on the surface. So everything that's missing here has been put into a pipe. And this shows with red lines where those pipes are. So these streams that were here are now piped and therefore never warming up. And if you were to take their temperature, they'd be running cold because of that. The exception to that would be, in many cases, these are also stormwater. So, and they're actually combined sewer stormwater operations. And so when it rains, you get a mixture of hot water from the surface as well as any sewer overflows, which would run hot. And this is not a modern phenomenon. This is something that dates back to the late 1800s in many of our urban areas, early 1900s. And it was just basically trying to clean up the urban area by moving your sewage out of the neighborhoods as quickly as possible. They knew exactly what they were doing. They did it on purpose. It's just we've outgrown that answer to pollution. You'll also see people talking about summer storms bringing pulses of heat. So this is a single storm event, and here's the change in discharge, and you can also have a change in water temperature. That's the discharge spike. This is the water temperature spike. This shadow here has to do with upstream water that was being released. What we generally find, though, is as you increase your impervious cover, you increase the number of days that have these surges. But most of these are relatively short-lived. They don't occur for a long time, and I don't think they're nearly as important as just the overall background elevated temperature due to deforestation, due to ponding. Last thing, and it's one that we don't often think about, these are data from Tokyo where they looked at water temperature. This is months of the year, starting in 1965, which is the open squares here, and going all the way to 2004, which are the filled squares here. And in essence, whether it's in the winter or in the summer, the stream is running warmer, and it's due to wastewater. And it's due to the fact that the wastewater today is warmer both in the winter and in the summer than it was in 1965. And they explain it to the increased use of heated household water. So if you were running on well water in 1965, and now you have hot water heaters, et cetera, your wastewater is running much warmer than it did in 1965. People don't think about wastewater warming up their stream. even if it's treated, it's gonna be running warmer. All right, last thing, climate change. So we've done all this thermal modification. Now we're gonna layer climate change on top. And I've added some images here. The top images are high emission scenario. The bottom image is low emission scenario. The left side is to 2060. The right side is to 2099. So what's going to happen sooner? What's going to happen later? Bottom line, if you just look at by 2021, in our area, the high emission prediction is about a 5 degrees Celsius increase on average. Low emission, 3.1 degree Celsius on average. The impact of that change is going to depend on where you're at. In other words, you notice there's different colorations here. Far more change up north, far more change in the higher elevations, for example. So Maine is different than Florida. This is what it looks like when you actually plot it on the map. And I put in 2 of these to show you. Here's just the migration of Illinois, pre-1990 to now to moving forward. And it's either high emissions or low emissions, high emissions being warmer. So Illinois today, or in 1990, is going to very soon, predicted to look like by 2021, South Texas. Northern Michigan has already moved to match right now the thermal regime of Southern Michigan. And by the 2021, it's going to be more like Kansas than it is Michigan. This is a different way of looking at it, and that is the conditions in Minneapolis are going to be down here, are currently represented in conditions in Oklahoma and Kansas. Washington, D.C., you're going to look at Arkansas, East Texas, Louisiana. Los Angeles, if you want to know what Los Angeles is going to feel like, go to Cabo San Lucas in the summer. That's going to be Los Angeles in the summer. And Portland is going to be Sacramento in the summer as opposed to Portland in the summer. So that's what a 3 degree or a 5 degree or a 6 degree average temperature means. That's how big of a geographic change you're going to be looking at. And the whole key is actually to remember that this is on top of all the thermal changes we've already done. So these are some models, May, June, July, August, September. The bottom line here is the baseline. That's what you start with based on modeling for projected water temperature in the absence of urbanization or climate change. Urbanization only is shown here in this line going up and down, the thick black line. Climate change only is laid on top of that, and it more or less matches it, a little less variable than urbanization change. The combination is the top bar here. This is what it means to be urbanized and faced with climate change. So instead of looking at, say, 22 or 23, this model is predicting that we're at this time looking at having water temperatures around 30. So that would be a full 8 degrees C. Now we know, again, it depends on the location, that we're already seeing 8 degrees. Bennett's Run is showing 7.5 degrees on average in July, August, and September. So climate change is going to go on top of that. So when we're thinking about climate change, we have to add in our thermal pollution from deforestation, from dams and ponds, from urbanized heat islands, from wastewater discharges, all coming into the stream warmer. So what do? What's our solution to this thermal pollution? Well, there's a lot of different things, and it depends on the site. But in 3 basic ways, what I thought is, first of all, we have to protect the cold water we have, protect our existing shade. If you have streamside forests, protect those streamside forests because they're doing something. They're keeping the stream cooler. The second thing is if it's not currently producing cold water, we need to reduce the amount of warm water we're producing. We have to drain or disconnect our ponds. We have to remove existing dams where possible. We have to increase our shade by planting trees, restoring forests. This is not planting one tree here or one tree there. This is about planting a whole lot of trees to provide adequate shade. Final thing is preventing warm water production in the future. We can't just blindly say yes to new ponds with standing water that's connected to the stream. We need to infiltrate our stormwater to recharge the groundwater, because that groundwater is cold water. And the more groundwater we have coming out, the more cold water we have coming out. So when you think about the stream restoration pyramid, and you've probably seen this, I've used it with you before. These are the 5 categories that some people, I don't like this pyramid, I don't like how it's formed, but I'm going to use it for purposes for you. And that is they have hydrology, hydrologic function, geomorphic function, physiochemical function, and then biological function. It breaks down to biology, chemistry, and temperature. Notice temperature right there, it's in this model. When you think about stream restorations as planned for you, they talk about geomorphology, they talk about hydrology, they talk about timing and quantity of floodwaters. They don't talk about temperature. And in many cases, what they do to design to restore these functions, they don't control for temperature. They put in ponds that make it warm. They hold water that make it warm. They won't put in trees because it messes up their geomorphology, but that makes it warm. So temperature is part of this discussion. It's clearly on the graph, but they think about temperature for oxygen regulation. I'm thinking about temperature as being just straight up temperature, a controller of physiological and physical chemical processes. So temperature is important to life in water. It's really one of the first things that pollutants we tried to fix when the Clean Water Act kicked in. We worked with power plants and dam operations. And here we are almost 50 years later, and what are we still working on? Temperature pollution. It varies naturally, diel, seasonal, annual, within a watershed, among watersheds. Be very careful about being too dogmatic. The temperature you see is where your sensor is. And it could be in a cold spot or a warm spot. And finally, we've already modified the stream. The temperature is warm. Climate change is going to make it that much worse. So one of the things that we can do locally is work to remediate our thermal pollution problems now, those local challenges, which means that as climate change occurs, which to some degree is not a local phenomenon, that waterway will be better buffered to absorb those heat changes. That's what I have for you guys today.
Excellent. Thanks, John. Do you want to, yeah. All right, so we are at 3:24. I would like to do our quick poll just for a minute or two before we take questions so that we can get this done. I'm going to launch that right now. So if folks could just take 30 seconds or so to complete this, that would be appreciated.
Be honest, not very useful, too deep or not deep enough.
Excellent.
All right, that's 30. We're at about 30 seconds. I'm going to end the polling now. Okay. Great. There's results. Okay. Okay. Questions for John?
Yeah, I have a question on the compensation, thermal conductivity or I'm sorry, electrical conductivity, the function of temperature. I've been using the charts that are on the standard bottle, and it appears to be linear. And is that true, or does the compensation of raw EC with temperature depend on what's in it and how salty it is, that sort of thing, or is it a simple linear function?
No, the temperature thing has to do with the sensor, not what's in the water per se. It's how the metals in the sensor are responding. To be honest with you, I don't ever worry about it. Use specific conductivity. In other words, it's adjusted for 25 degrees C. That's all anybody does. You have to adjust for temperature. There is a graph, and it wouldn't surprise me if there were portions that were nonlinear. But the most important thing is don't screw up and use anything other than temperature corrected conductivity. So only pay attention to that number and only mess with that number. That's the only way to talk about it between sites and between seasons.
Okay, I think I understand. It was just my own personal problem. My sensors are doing the raw sense data, and I need to correct it to 25C. I'm just using what's on the calibration bottle, which seems to be sort of linear.
It probably is, and that's probably fine.
Okay, thanks.
John, there's a question from Michael Johnson. Are there efforts in PA to respond to temperature problems with stormwater retention?
You know, they're more aware of it now than ever. You're seeing more infiltration. It's not always, remember, in your urban areas, you don't have trout anyway, and trout is what everyone talks about. So they pay less attention. What they're coming to grips with, though, is again, you can reach thermally lethal temperatures that even for something that's not a cold water fish. And the other thing is that toxicity often increases with temperature. So this idea of stormwater ponds and what they are or are not it's a real mishmash of philosophies. Are we controlling for volume? Are we trying to filter out pollutants? That's why temperature falls off the discussion map. They're having a hard enough time dealing with pollutants and volume. Are we preventing flooding, or are we trying to absorb all of the nasty stuff that washes off of our urban environment? And so there's no single answer. One thing I will tell you, though, is that they also know that urban streams tend to have lower base flow, and that's because they're not infiltrating enough of their rainwater. Once you decrease your summer base flow, then you have an even greater thermal effect because you have a smaller volume of water to change with the same amount of energy that you're there. So it absorbs it and the temperature range can be greater. So that decrease in base flow not only decreases your dilution capacity, but it increases the probability that you're going to reach higher temperatures on hot days. So it's a double negative. Recharging through infiltration is a double winner. You get the filtration effect and you get increased summer base flows.
Okay, let's see, there was another question here. Would temperature affect, from Walter John, would temperature affect microbe populations which might close beaches or limit public use?
Yeah. You know, no one wants to say whether your fecal bacteria can reproduce outside of the human gut. But absent of that, of course, you're going to get more algal blooms at warmer temperatures. So we'll go to the toxic algal blooms, the hazardous algal blooms. And yes, you increase temperature, you have a better chance of having a potentially hazardous algal bloom. And they know that. And so they are correlated. And that's, I think, a prediction of one of the things. See, and that's very hard because those are large lakes that serve a socioeconomic value in a community. They obviously have a nutrient problem, but there's no way to shade it. That's going to be straight up climate change and urban runoff warming.
Okay. Let's see, are there any other questions here? No other questions in the chat, it looks like. Any other questions at this point for John? Or questions on anything else? Questions about stations?
Actually, let me ask you guys a question, and don't be afraid. I have a very thick skin. When somebody scored that it was kind of helpful, if you pull up the survey, Dave, it was, it was, my question was, when it was kind of helpful, is it redundant? Or not very useful, or somewhat useful? Is it redundant? I'm just curious, what would have made it more useful, just so I know where you're coming from? And maybe it's just, I'm not that interested in temperature. I'm more interested in how to get my communication board to not go on the fritz. So whoever said that, I'm not hurt by it. I just want to make sure I understand if there was something that would have been helpful. I can write myself a note and cover it at another time or in a better way.
Well, I'm going to speak up. I didn't take that poll, but what was in my mind was, it's fundamentally very important information. And I know, looking at the sensor data, that temperature is increasing on the two reaches that I've been looking at every season, every year. But I don't know how do you get a a government agency or something to care that the temperature is increasing? How do you get them to appreciate the significance? That's just what was going through my mind, is how to make it connect.
Yeah, that's very interesting. And that's our next challenge in working with you guys, and how to package this in a way. And one of the reasons why I threw that restoration pyramid out is to show you that, stream impairment, for example, is almost 99% a biological phenomenon. It's you've killed bugs or you've killed fish or both. It may be some consumption things or recreational things that are also involved, but 99% of the time it's a biological impairment. Yet, and temperature, without a doubt, is playing a role in that. In other words, most of your warm water fisheries used to be a cold water fishery. So the first thing you know for sure is it's too warm to be a cold water fishery. And is that an unreasonable restoration? Well, what we know here, and as an example at Stroud, White Clay Creek at Stroud, we have wild trout. But I guarantee you those trout, if they were there, were very unhappy in 1900 because the stream was in far worse shape. Half of the water was running in mill races, things like that. So it ran hotter. It would have been a struggle for trout. So it can recover. There are things we can do. And so our research and restoration program are trying to push the envelope. We've restored very, very few streams. In many cases, we've restored them accidentally. And that's what White Clay Creek at Stroud is. Nobody made a plan between 1850 and 1950 to clean it up. It just kind of happened. But every one of your streams that is not in 100% forested watershed has that history of self-repair when we finally quit messing with it too much. And now our goal is to recreate that. Well, one of the things you think about when it happened passively, what did nature do? Nature didn't get bulldozers in. It didn't pretend like it understood the hydrology and stuff. It kind of just stood back and fixed it. So that sometimes I don't have answers for next steps where the red flag is, but that's where the research is working. And those of you who know my work with salt, one of the reasons why I'm less concerned about spikes in the winter than I am about high base flow salt in the summer is because the temperature difference is 20+ degrees, and toxicity doubles to quadruples every 10 degrees. So the toxicity is probably a bigger issue in the summer than it is in the winter, summer, early fall, than it is in the winter because of life histories and the elevated temperature, the seasonal differences. They can't get away from it. In the winter, their metabolism is so low that 24 hours or 10 hours or 5 hours of that spike, they're not happy. And I'm sure there's some mortality, but that 60 days of constant hot weather in August and September and all the groundwater is salt laden, I think that's a bigger stress. We have a few more questions here, Dave.
Sorry, I was muted. Michelle de Blasio is asking a good one. When collecting continuous temp data, what is the value of collecting data every 15 minutes versus 30 versus 60? What do you lose or gain by changing the interval at which data are collected?
It depends on as much philosophy as anything. Are you a big data person? You know, we did a whole lot of science looking at paper charts and grabbing temperatures once an hour. But on the flip side, there are these different events, and you can miss an event, an hour-long event. So I'm not going to throw it completely under the bus, but in something that's structurally like water temperature, you don't lose a lot going from 5 to 15, and maybe even 15 to 30. 60 can get a little tricky though, because weather actually can change hour to hour, and you can go from bright sun to clouds and not know it. Next one, specific heat. Oh, you know, it's funny. I didn't add the specific heat until this morning. And that's because specific heat is one of the first things you learn as an aquatic ecologist. So it's in the back of my head, and I just take it for granted. And then I remembered why it's so important for life in water and the stability of water temperature due to the high specific heat of water. So that's why I added it in. But if you Google it, there's a lot of very basic stuff out there.
So John, maybe think about any particular papers for Michael, because he's really diving pretty deep into the science. So I'm sure he would appreciate actual peer-reviewed papers.
I don't have any peer-reviewed. Everything I ran into, I know this sounds really awful, but it looked like middle school science graphs and stuff. And that, to give them credit, they produce some of the best graphics. I mean, they spend a little money, they add color and big letters, and for my old eyes, it makes a difference. But if you go to any library and find a basic limnology book, or go buy a basic limnology book, there will be a section in the very beginning about physical properties of water that will get you started on some of this stuff. And but some of the science is going to be really old. That map of groundwater temperatures, for example, that's a modification off of a 1910 map. Everybody just keeps going back to the old map and redrawing it with better graphics, or going from Fahrenheit to Celsius.
Okay, so Grace has a request here. She wants to know about talking to local officials and how to communicate simply about these temperature issues, pretty much talking about how to produce a red flag, or talk about red flag in terms of temperature.
Well, it depends on the stream. That's one of the tricks. So if you're lucky enough to be in an area where protecting trout is a goal, then paying attention to that is important. And that gives you a management line, not to exceed type of thing. I've been working with Dave trying to locate some other thermal characteristics for some other fish, common fish and things like that. And we haven't had a lot of luck. But those are the things that I'm looking for right now. Believe it or not, the Stroud Center has been doing research on temperature since its beginning. It's so elemental to what we do. It's so important to understanding life histories. But I don't often talk to it. That's why I worked and did this twice. I was so unhappy with my last presentation. It was so much information. I did a data dump on you guys that was unfair. Biology, ecology, physiology, and the physical characteristics of water temperature. So I tried to split it up. There's more to do on that. This is not one we've talked about well. We talked about it when it was power plants, and it was easy to illustrate as a problem. We haven't talked about it well. As an example, that paper I just showed you by my friend who's at UMass, that was a 2021 publication or late 2020. It's that recent that someone put a hobo above and below small dams just to measure the impact, the thermal impact of different small dams, and doing it enough times to talk about what characteristics influence the thermal impact of dams. And I thought it was brilliant that she found that once it gets a certain amount of heat, the dam doesn't matter. The thermal pollution tied to deforestation and everything else going on in that watershed made the dam insignificant. That water was holding the amount of heat that it could handle, more or less. That was new. And 50 years after the Stroud Center started, looking at temperature.
Okay, we are well over our stop time. It sounds like seems like people have really valued this topic, though. So thanks, John. Any other questions before we end the meeting here today? All good? All right. Well, everyone, please be in touch as needed regarding your stations. Take care, be safe when you're out in the field, and feel free to be in touch with us at Stroud as needed, all right? Bye all.